Hello everybody, my name is Bill, and today I'm going to talk about AVL tree. AVL tree actually is a self-balanced binary search tree. So there are several concepts should be talked about later. So let's talk about why there is an algorithm called AVL tree. This AVL comes from the two scientists who invented this algorithm and the very beginning letter of their names. So let's just dive into the content that we should talk about today. And first of all, I want to talk about what is tree, what is binary tree, and what is binary search tree, which is called BST. And eventually, I will talk about AVL tree. So what is tree? Tree is very commonly seen in our daily lives, and and of course, for a tree, it has roots. Of course, in this situation, the 15.6 node is a root node, and 15.6 is the key for this node. So the value is the key. And these two connections, let's just open up a pen. And these two connections belongs to the is called edges. And these edges were connected to the children. And then in this situation, their relationship between the 22 node and 14 node and the relationships called siblings. And these three triangle nodes is called a subtree of the 22 tree. And the number 11 tree is the parent of the number 3 node. And the number 3 node is the children of number 11 node. And I'll talk about the leaf nodes. Why it's called the leaf nodes? Because it had no connection, no edges connected to its children. So it's called just a leaf because it has 0 children. So later on, we'll talk about the head of the tree. So this one is very important for AVL tree because it's a concept that has been used in AVL tree. So head of the tree basically talks about the numbers of the levels of each node. For example, this is a first level. In the first level, there are 4 nodes, and for each node they had number 1. But for the second level, for example, like 16.5, there will be 2. The head will be 2. And the 16, the head will be 3, there'll be 3. So you got an idea, right? Later on, we'll talk about binary search tree. So what is binary search tree? I think you may already learn the binary search. For the binary search, it's actually an algorithm for search. And the good news is the time complexity of the binary search is big O log 2n. So in these algorithms, it requires already ordered sequence, and you will search half. You will search halfly, right? So, for example, if less than the current node, you will search the left part. If a bigger one, you will search the right part. And the same as the binary search tree. Actually, you can see from the name of this kind of tree, it has a search in it. So, which means it tries to facilitate search operations. So how do you form a binary search tree? Actually, I forgot to talk about the binary tree. Actually, the binary tree is quite simple. It just defines a tree that their maximum number of edges should be 2. So up to 2 edges for each node. So the node could be 1, right? In this case, it's 1 edge. Could be 2. Could be 0, but not more than 2. Okay, let's continue to talk about the binary search tree. So how to form a binary search tree? For example, if you have a sequence like this, right? You have a 15.6 and put the first one as a root, and then the 30 put the left node here, and then 22. 22 is less than 15.6, right? So it will belongs to the left subtree, and then still less than 30, so it belongs to the left subtree, and then find the position here. And then 17, and 17 bigger than 56 will be put into the right subtree, and this is the first node for the right subtree. So we'll be put it here, and then 40 less than 56 left, and bigger than 30 becomes here. So basically you got my idea, right? Okay. This is the very basic concepts of tree, binary tree, and a binary search tree. We already have such a BST, but this BST not called totally imbalanced, but it already be quite. You can see from the appearance of this tree is a little bit balanced. It's already a little bit balanced. So in this case, if you want to search a node, for example, if you want to search the 40 node, you just find 40 less than 56, and you'll find the left part, and then you will find 30, and compare 40 to 30. If 40 bigger than 30, you will pass to the right subtree, and you'll find the 40 node, right? So in this case, you can reach if your tree is as balanced as much possible, you'll get big O log 2n. But what if your input sequence is already ordered? For example, like 1, 2, 3, 4, 5, 6. And in this case, you will get a very weird binary search tree. So in this case, you will have 1, 2, 3, 4, 5, 6 in a line. So in this one, you get very weird binary search tree. It's totally imbalanced one. For example, if in this case you want to search the number 6 node, you will find the first time, second time, third time along its trajectory to find the number 6 node. So it's not easy, right? And in this case, the good property of big O log 2n becomes log n. This one is totally suck for search, right? So in this case, if you have a slow search, then you have a slow insert and a slow deletion operations, because the insert operation and delete operation depends on the search operation. You should find the node first, so it will totally affect the efficiency of the algorithm, right? So how to correct this? Actually, correct this one is correct. How to solve such a problem? So this is AVL tree came into being, and AVL tree, still remember that is a self-balanced binary search tree. So it's a binary search tree. So it tries to, so the algorithm always can find a way to balance such a weird BST into a balanced BST. So it's very efficient, and we will talk about the details later. Then we will have big O log 2n search. It's just like a binary search, right? So in this case, we have a AVL tree. So before I talk about AVL tree, I talk about the two contributions, main contributions of this paper. So the first one is introduce a balance factor. So what is balance factor? This is a definition. Actually, this is a DEF for the balance factor. Balance factor is defined as the head of right subtree minus the head of left subtree. And we want this BST become balanced, so the absolute value of the balance factor will be less than 2. So which means there could be -1, 0, and a +1. So this is a figure that this example shows different nodes with the numbers indicating its balance factor. For example, like this is a first level. The first level, so the head of the tree will be 1, 1, and the right minus subtracted the left will be 0, and this one will be 2, and this one will be 1. And for the V node, 1 minus 2 would be -1, right? So you will get an idea of the whole process. And the second one is the AVL tree defines a set of rotation operations depends on different situations. It's called RR, LL, RL, LR. So this is in this case, R and L represent right situation, left situation. RL is a right left situation. I will talk about details like tongue twisters. It's hard to pronounce, but you got my idea, right? And a little bit counterintuitive in the first two cases. In the right situation, you should perform a left rotation, but in left situation, you perform a right rotation. But the later two cases is very intuitive. It's RL, but so you perform a right rotation first and then the left rotation. So which means it's a combination of two rotation operations. Okay, let's have a look at the dynamic graph. This GIF is from Wikipedia, so you got the basic idea of it. Whenever you want to insert a node, after insertion, and the AVL tree will check its Bennis. If a node has a Bennis factor that bigger or equal to 2, there some operations will be performed. Actually, when you written code, there is no chance that the Bennis factor will larger than 2, because each time it equal to 2, it already performed operations to correct the imbalance. So I will talk about the details later. This is just give you a very basic very basic ideas of it. Okay, let's talk about the tips of the AVL tree. I have 3 interesting conclusion about the AVL tree. This is the take-home message, so please be careful about this part. You may not find these tips in your AVL paper because it's informal, right? I just mention it to help you memorize the whole process. Because if you just look at paper, it's hard to understand. It's hard to memorize all those details. But within these 3 tips, it's easy to understand the whole process of it. Why I put these star marks here? Because the first one is the most important one. You should find the correct classification. You find in these 4 categories, right? The 4 categories corresponding to the column of this figure, it have different performs. Have different operations should be performed. So this is a combinations, and this is a single one. Later 2, once you got the first one, right? You have the specific situations. You will have later on tips for each specific operations. So the second one and third one actually is for the details of each operations. Why I call it takeover for the left rotation or right rotation, because in these 2 operations there's a process that a node should take over a position of another node, and then another node should find a new position to fit in. So why I call it delegation? Because in these 2 cases, there are a combination of the rotation operations. So the first rotation, in the first rotation, the very root nodes won't do the dirty work. They will let the second hand do the dirty work. I will talk about later. So the delegation is very vivid, right? Analogy for you to understand and for you to remember. So just directly dive into the specific cases. First, I will talk about the left-left situation. The left-left situation corresponding to the second situation in this figure. So actually, there are 3 cases could be mapped to this left-left situation. So why it called the left-left one? Because for example, in this figure, this one is in the first floor, in the first level, and the head of this node will be 1, and the same as this one. So Bennis factor of this node will be 0. Bennis factor for this one will be -1, right? Because it has a 0 right cell tree. And for the number 3 nodes, it will be 2 in the left subtree and have 0 in the right subtree. So basically, it has -2. It is because of this tree, and this tree is the left node. Actually, the same as the second case and the third case. In this whole graph, every node is in a balanced situation except this one. So this one, the balance factor would be -2 because in this one it will be 3, right? This one is just 1. So in this case, it will be -2, same as this one. So there's some certain operation should be performed. Let's have a look at the very simple case for the LL situation. In LL situation, there should be a right rotation performed. So for example, if you add a number 1 node here, and then they will fall in imbalanced situation. So number 3 node will take over the right part of the number 2 node. Even there isn't any right subtree for the number 2 node, but still there is a null subtree. If you write the code, you understand what's going on. I will provide you a code later. I will put it into description below. You will find it in the code, right? Okay. So the number 3 node will take over the null node. Eventually, you will form a triangle, just like it's quite easy to understand. It's just like a chain that you lift up the middle part of the chain, and this part would eventually fall down to this position, right? So it's quite easy to understand. So let's have a look at the dynamic graph, and you will see if you want to insert the number 1 node, and you will form a situation like this, and the number 3 node will find is imbalanced. Let's see again, update the head will become 2, and the head of number 3 node will become 3, and then a right position will perform. So eventually it will become a triangle. Okay, let's have a look at the second case. In the second case, you can see that a little bit more complicated, but it follows the same rule. Okay, in this case, every node is balanced except this node, right? So this node has a 3, 1, so the balance factor would be -2. So in this case, a right rotation to be performed. Number 6 node should move to the number 5 node here, and then take over the number 5 node. And number 5 node there's a number 5 node, right? Number 5 node has no position to go, and then they will attach to the left part of the 6th node. So what happened? You can see that the number 5 node is always bigger than 4, right? Because it's always bigger than 4 because it's attached to the right part. In a binary search tree, for every node, every node in the left subtree is always less than itself, right? The same as the right part, but the right part is always bigger than itself. So it's less than 4, but bigger than 6, bigger than 4, but less than 6. So it could be attached to the left part of the 6. It's just like there is a quite interesting analogy for you to remember. It's just like you sit in a library or sit in a cafe to drink coffees, but you just leave for a while, and later on you come back, you find someone took your position, right? So in this case, you may be angry, but you are a polite person. You will find a correct position for you to stay, right? Later. Okay. So this is a dynamic GIF image for you to understand. For example, like if you want to insert a number 2, first you should search which position to put, and eventually we select here, update the head along its trajectory, and then perform a rotation, and then just put the number 5 in the left part of number 6 node. Okay, let's have a look at the third cases, left third cases. So basically, it's a very similar as quite similar as the second case. Number 6 will take over number 5 here, and then number 5, actually there's a 0005 node here, and it will find the correct position. So where should it go? Actually, number 5 is bigger than number 4, right? Otherwise, it won't be hind to the right part of the number 4. So it will always bigger than number 4, so it should be go into this branch, and then always less than number 6, so it should be attached to the left subtree, because this subtree, left subtree, always less than the root, right? This is the rule for binary search tree. So basically, it performs quite. It should be placed here in third case. Also, we have a look at the GIF image here. So if we want to insert a number 3 node, we'll find the correct position, updating the head along its trajectory recursively, and then to change the banners. It's quite simple, quite easy to understand, right? Okay, so let's dive into the implementation of the whole process. As I mentioned, I provide a code, which is here. I provide code just to use the online compiler, and the code I will put it in the description below, and you will check it. Usually, when you learn something, the correct path is you should find intuition of the algorithm first, and then you try to find a code you can debug one line by one line. So in this case, you understand the high level intuition of it, and then understand the details of it. So in this case, my code is written up absolutely in Python, because Python is easy to understand. It's good for algorithm. Okay, let's have a look at this. In AVL situation, you will have node. So currently the node is 0006, because the 0006 has the -2 Benz factor. It should be rotated. So the first 2 live code is just defines the node right and node. So let's have a look. It assigns the pointer to the node to the node right. Okay, so what's going on here? Okay, sorry for it. Just close this one. Okay. Yes. Okay. Alright, wait a second. Okay, the first line is the pointer of the node assigned to node right. Right. So this one is also called node right. Okay, sorry. I just give it a pen first. So it becomes node right for the number 6 node, and node dot left, which is number 4 node, right? Number 4 node assigned as node. So it's quite simple and intuitive. And the second part is the most important part. Intuitively, we want the number 6 node take over the number 5 node, right? And a number 5 node will be attached to the left part of number 6 node. So this is the whole process. Actually, the second, in this slide, these 2 lines of code do the stuff. Okay, let's have a look. Node dot right. This is a node. Node dot right is number 5 node. Number 5 node assigned to the no right dot left, no right dot left. So this node breaks down this pointer. Actually, this belongs to this pointer. So basically, it splits the two graphs, and then the node right, which is the number 6 node, assigned to the node dot right, which means this node has been attached to this direction. Okay, it's a little bit ugly, but you can understand my idea, right? Okay, so the idea, so the codes basically complete this process, and you can find it in my code and debug by yourself. It's easy to understand. Okay, later on you will want to update the head of each node. So basically keep the head of each node up to date and for the later use. Okay, let's finish talking about the LL situation. Let's talk about RR situation. RR situation is the right situation. It's actually the mirror case of LL. So basically, it's just a shift direction, but everything almost the same. So in this case, the benefactor would be be positive 2 because there is 0 here and there's had 2 here. 2 minus 0 would be 2, right? So in this case, this node is the problem node, right? This is the right subtree and a right subtree, so it's called a right situation. The same as this one, the right one and the right one. So in this case, just perform a mirror operation as the LL situation. So it's not much to talk about. Okay, let's just skip the LL1 and talk about the RL1. So this one is a little bit complicated than the former mentioned cases. It also has three specific cases. So this one belongs to this one. It's a combination of rotations. For this case, for number 1 case, you will have a number 2, number 3 node, and it has the head of a right subtree is 2, and 0 head for a left subtree. So basically, the balance factor will be 2. The same as this one. This is a problem node because this node is imbalanced, right? Because of this node. So it's a right and left one. It should perform right rotations and left rotations followed. And the same as this one, it's a balance factor equals to positive 2. So this one and this one, the head of this one is positive 1 and this one is a positive 3. 3 minus 3 substitute 1 would be 2. So balance factor would be 2. There are certain operations to be performed to correct this imbalance. Okay, let's talk about the first cases. This is an interesting notation I introduced here is a chrome, right? Is a king chrome, because I have mentioned before for those two for those two situations, I define a delegation for easy memorization. Just for this one, why I call it delegation? Because for this node is imbalanced, but it is a king, right? So there's a combination of two rotation operations. In the first operation, the king won't do the king or boss won't do the dirty work. So like the second hand to do the dirty work, like vice president do the dirty work, and then the second hand would take over, would get this power to do some rotations. And the first thing is to do the right rotations. So in the right rotations, these two should be rotate 90 degrees. So we form like this one. So the 0002 will take over the 0003, and 0003 will becomes the right subtree of the 0002. No, so it becomes this one, And in this situation, it's very familiar, right? So it's a right situation. It's easy to it's easy to perform because I already mentioned that before. They will eventually form a triangle, as we discussed before in the previous situations. So what about the second case? The second case is a little bit complicated. You think it's complicated, but actually, if you divide it into small pieces, it's still easy to understand. For example, this one, the balance factor would be -2. But because of this node, right? So it's a still right-left situation. And in this situation, a right rotation, a left rotation should be performed, and the king will delegate its power to his second hand. And this is the second hand, right? So this subtree will have a right rotation. So how do the right rotation? The number 8 node will take over the root of subtree, and then every node just follow. For example, like the 10 will be attached to the right tree of the number 8 node. And then the king find is the right time to do something, right? It's already been balanced, this subtree. So right time to came into do something. In this case, it just perform a left rotation because it's an R situation, right? The number 6 node will take over the number 7 node, and number 7 node will find nowhere to go and find the correct position to attach to the right subtree of the number 6 node. So eventually it will become this formation. For the third situation, for the third cases of the RL situation, it's almost the same as that one. But in this case, the first step, the king will delegate the second hand to do its job. So we should understand. We should perform some operations in the subtree. In this subtree, the number 6 node will perform a right rotation to substitute the number 9, because if number 8 becomes the root and number 10 would attach to the right part. And so which is the right position for number 9 node? Because number 9 node is bigger than 8 but less than 10. So it should be attached to the left part. Yeah. So in this situation, we still find that is a right situation because this node is still imbalanced, but because of this node, right? It's a right situation. In this right situation, you just leave just like chain. You leave this node up as the root, and then the number 6, number 5 just follow the number 8 to fall down to this part. Is just like this. Yeah. Okay. We already discussed the every situation mentioned by this paper. So let's have a look at the right and left situation and its code. Actually, its code is quite simple. It's not as you think is hard to do, because we already defined the right rotation and left rotation. And RL situation depends on these two rotation operations. For example, if you want to rotate the root node, and you already know that root node is the king, right? So the king will delegate his right one to do the right rotation first. And then after the dirty work has been done, the king think, oh, okay. The boss will think, okay, the situation already been handled, and I could do something the right time, right? Okay, so the left rotation will be performed later on. Let's have an intuitive understanding of it from a GF figure. So this is one. For example, if in this situation is a RL1, and then will be performed right rotation to get the RR situation, and then they're followed to get a final state. Okay, so this is a last situation we could talk is a left-right situation. In the left-right situation, it's a mirror case of it's a very mirror case of RL. So in this situation, for this node, is Bennett's factor for this one is -2. For this one is -2 as well. For this one is -2 as well. It's because of the left and the right children. So just as the same as I mentioned before, in this case it's quite easy to handle. So so far it's good, right? We already talked about 4 situations defined by the AVL tree. So we talk about simple rotations, we talk about the combinations of 2 rotations, and we also saw the dynamics figure, also saw the codes, right? So far so good. Let's have a look at a specific insert example. For example, if we have a sequence like this one, right? First we have a 12 just placed here. Later on, we have 4. 4 will, because 4 is less than 12, so will be placed here. And then 1 will be placed less than 12, less than 4, so the correct position for number 1 node is here. But you already noticed, right? It is imbalanced. This is a LL situation. For this LL situation, it should be performed, right rotation be performed. So eventually it will be performed at triangle situations here. Later on, we already mentioned that 3 node, right? So the number 3 node is number 3 is less than 4 but bigger than 1. So the correct position for number 3 is here, and but still balanced. The tree is still balanced. And then you'll perform a number 7. You will insert a number 7 node. And number 7 node is bigger than 4, less than 12. So the correct position for this one is here, but it's still balanced, right? But for the number 8 node, something happened. Number 8 node bigger than 4, less than 12, bigger than 7. So the correct position for number 8 node is here. But thing is different. You can see here it's different. It's familiar because it's an LR situation. You should perform a left rotation for this one because of delegation by king, and the right rotation later on. Eventually, you will have 8 as the root, and 7 and 12 as left and the right child of the number 8 node, respectively. So basically, this happened. And later on, we have number 10. Number 10 is bigger than 4, bigger than 8, less than 12, so will be placed here. So the whole tree is still balanced. And followed by 9. Number 9, bigger than 4, bigger than 8, less than 12, less than 10, so becomes insert here. So in this case, it performed an LL position, LL situation. In LL situation, right rotation should be performed, right? Eventually, just put in number 10 as a root node, and this 2 node attached to the left and right, respectively, right? Okay, so far so good. We have number 2. In number 2, we have we insert the number 2s here, number 2 node here, and then this is a RL situation. In RL situation, there is a delegation process will be performed, and eventually will form a triangle here. And this is a complicated situation. Actually, this is not the most complicated one. If you have 11 bigger than 4, bigger than 8, bigger than 10, less than 12, so be placed here. This is a special case for our left rotation should be performed. Number 8 should take over the number 9, and number 9 should find its correct position and attach to the right part of the number 8. So basically, it performs like this, and number 10 node becomes the root of this subtree. Okay, here we go. Comes the most complicated part. Number 6 have been inserted. Number 6 bigger than 4, less than 10, less than 8, less than 7. So correct position for number 6 will be placed here. Do you notice that number 4 is imbalanced because this is 2, there's a 4, so the balance factor will be should be positive 2, right? So it's already imbalanced. In this RL situation, we mentioned before, it should perform a right rotation and left rotation followed, a delegation first, and then the 8th node should take over the 10th node position. So 8th node should be the root, right? Should be a root. And then the 10th node will be attached to the right subtree. So it will take over the number 9 node. The number 9 node loses position, so you'll find the correct position because it's bigger than 8, right? Bigger than 8, so it belongs to the right part. But less than 10, so you'll be put here. But it's still imbalanced because the king hadn't do anything currently, and if he thinks that currently is the boss thinks the currently has the right position, he could do something. Then a right position could be performed. A left position could be performed. So the number 8 node becomes the root, and number 4 node will be attached to the number 4 node. Could be the left part of the number 8 node. So basically, you will take over number 6 node, and number 6 node will be attached to the number 4 node. You already seen that, right? And here comes the last number of this case. The last number is the number 5. Less than 8, bigger than 4, less than 7, less than 6. So the right position is here. So in this case, is a LL position. In LL situation, a right rotation should be performed to form the last case. So this is the final BSD tree. Okay, let's move on to see how it performs by insert those sequence using our code. My code will be put in the description section below. So the result is the same as this one. As we can see that 1, 3, 5, 7, 1, 3, 5, 7, 11, 2, 6, 9, 12, 2, 6, 9, 12, same as this one, right? We could perform a run here. We already comment those deletion codes and then run. I think, yeah. So the result shown, right? The same as this one. 1, 3, 5, 7, 11, yeah. So it's the same as this one. So what about deletion? In deletion, they'll be a little bit tricky because in AVL tree is a special case for the BSD tree. In BSD tree, there is a deletion operations. In the BSD tree, for example, if you want to, in this case, you're already a BSD tree, you want to delete a number 15 node. So how do you delete it? As we all know that in the binary tree we have 3 iterations. It's a pre-order, in-order, and a post-order. And for each BST, the in-order recursive, you will get a sequence in order. For example, like in order is the node, left node first, and then the root node second, and then the right node the last. For example, like the first node is 1, 1, 7, 14, and then 15, and then 15, and then 16, and 28. You get my idea, right? So basically, it's follow like this, and then this. So you will find the most the number just bigger than the 15 or just smaller than the 15. So which means there will be 14 and 16 could substitute the 15. So you can choose either way, the 15s or 16 to substitute the 15. In this case, we choose 16 to substitute it, and then there will become the 16, and then delete this node, delete this node, right? But you can see that in this case, this node, okay, you can see that if you use the 16 to substitute the 15 and delete it, and deletion will be complicated. It will be complete. So here is a dynamic GIF figure for it. For example, if you want to replace it, then replace the value first, and then find the correct node to delete, and then delete this node, and everything has been done. Correct? So what about in the aforementioned case? So what about if we want to delete the number 10 node? Actually, you have two choices. You can use the number 9. It's the very right node in the left subtree, and the very left node, which is number 11 node, is a very left node in the right subtree to substitute the number 10. If we directly choose the number 11 to substitute number 10, you are directly to form this one, right? We'll delete this one. But if you want to use number 9 to substitute number 10, they will form a RL situation. So in this RL situation, you should perform a corresponding right rotation and left rotation, and eventually you will get the same result of this one, right? So let's have a look at the GIF figures here. In this case, you choose the left subtree to substitute this node, and then perform a rotation and then update its head. But usually in the AVL tree implementation, there is a comparison to compare the left subtree head and the right subtree head. So in these two heads, you'll compare it to choose a larger one. For a larger one, it has more depth, which means you have more chance to do less operations, to do less rotation operations. For example, in this one, if you choose 11, there are no rotation operations should be performed. But if you choose the number 9 one, you should perform 2 operations, right? Actually, we could see the code here. We could see the code here. If we find these nodes, we don't do the rotation. We don't do the substitute first. We should compare the head of the left and the head of the right first. If the left head bigger or equals to the right, and then do the following part to find the very right node, or we could choose the second row to find the very left node in the right subtree. So this is the case. Okay, so in our code, in our code we could find we could get the correct result. Same as this one. This one is oh, I forgot to mention. All those figures and the processes are there is a website called a AVL tree visualization. I already listed in the previous slides. You can find it. So my code could perform the correct result. For example, like 1, 3, 5, 7, and this is a 11, 9, 12. There will be null nodes here. So null nodes here, null nodes here. There's no nodes, so it'll be a leaf, right? Leaves. So everything performed quite good. So that's good. Okay, let's have a look at the code. For example, if I should delete the number 10 node, I just uncomment it and I print it again. Run the code. You can see this is the very beginning code after insertion, and this is the tree printed after deletion. You can see that the number 10 node has been deleted successfully, and number 11 node substituted it and it become balanced again. So it has been implemented by code. You could find this code in the in the description below, and you can debug it line by line and see what's going on to add a breakpoint in the code, because it's the most efficient way to learn an algorithm. You learn the very basic intuition first, and then followed by the code. Okay. Last but not least, I will talk about the complexity analysis. This is quite important because even you introduce a new algorithm, but it has a very worse, very suck complexity. It almost it will make your operations become very complicated and not easy to use. It's not good, right? But for the AVL tree, it has very good property. AVL tree is a special case for the BST, and BST is a very widely used one. Because I'm a computer science PhD student, I've done some research in reinforcement learning. If you are familiar with this field, you will know that there's a DQN algorithm. In DQN algorithm, there's a variant called prioritize experience replay for the DQN. In that algorithm, BST has been used in it, but of course it's called a sum tree, but it's a BST. Anyway, for the AVL tree, the height of AVL tree always be the big O log n. Of course, the base will be 2, right? And the n is the node number. Just as a binary search, it's just because the height would be the big O log 2n. So the property of search, insert, and the deletion will be all of them will be big O log n. Whatever is average case or the worst case. So it's quite good property. And again, the complexity analysis is very important for algorithm. I have mentioned before. Okay, so basically this is the all the content I talk about today. Thank you so much for listening.